Well, good morning, team chemistry coach coming at you. Whoop whoop. Crazy shirt. So, we are going to be talking about a pretty important topic that you're going to run into over and over and over called Hess's Law. Lots and lots and lots of times we're going to use this in second semester general chemistry. And we've actually seen this if you've taken my labs. We've already applied, oh, it just hit my knee. We've already applied this concept in lab. If you had my labs, you might remember one of the tests we used, the barium hydroxide test, to test for the presence of carbon dioxide gas, or I think it was sulfur dioxide gas. I made you do all the reactions that showed that precipitation of the I think it was barium carbonate or something like that. And so we had like a bunch of reactions that occurred, and we added all those reactions together to get this overall equation. That's one application of Hess's law, right? So I put down kind of a defined, wordy way of looking at Hess's law. The next board, let's look at it pictorially. Sometimes the pictures are easier, even though I have to explain it. But for pure just thermodynamics, we're going to look at it in terms of equilibrium and kinetics next semester. But for thermodynamic state functions, remember a state function, like enthalpy or something like that, we can't determine the enthalpy specifically, the absolute enthalpy of a system, right? But if we have a system at state 1 and a system at state 2, we can determine the difference between those, right? And it doesn't matter how we get from state 1 to state 2. I'm going to do that diagram in a second. We can do that by multiple different pathways. That's what a state function is. That delta H wouldn't change once state 1 and state 2 are defined. So for enthalpy, which is our focus here, our goal again is to take Hess's law and indirectly calculate a value for a heat or enthalpy of reaction, right? Theoretically. It's not always easy to do experimentally, but Hess's law is going to allow us to go like through the back door, indirectly calculate values of delta H reaction. But this is just a tiny specific application of Hess's law. This is a very broad umbrella term we're going to be applying to many different things where we want to get from this state to this state, and we can do it by many different pathways, not just with calculating heats of reaction. So it can be for any process or reaction, okay, where we're trying to get this overall enthalpy change. What's great about Hess's law applied to the thermodynamics is the overall enthalpy change of that process is just the sum of the individual steps. Whether it takes you 5 steps or 2 steps or 3 steps, doesn't matter how you get from here to here, that difference will always be the same, okay? So all we have to know is the values for each individual step, add them all together, wada bing, wada boom, we've got the overall enthalpy change. Oh, we're going to be doing things like Born-Haber diagrams next semester, right? Yay, I love those. So let's take a look at this pictorially with some enthalpy diagrams real quick. I think it makes a little more sense that way. All right, we like pictures better than words, right? Let's take a look at 2 scenarios, all right, using Hess's law. So let's say we have some system at state 1, and we get it to state 2. And what we're after is the difference. See, this is the enthalpy. We don't know the enthalpy for state 2 or for state 1, but we could calculate the difference between those, right? So let's look at that. So this is the delta H that we're looking at, right? So we can do this from pathway 1 or pathway 2, but it's the same regardless of what pathway we take. So this is going to be delta H. We'll call this overall in both scenarios. My ugly little triangles there. So regardless, delta H overall is going to be the same regardless of how we get from state 1 to state 2, right? Yay, state functions. So let's take a look here. Let's say in the first scenario, pathway number 1, we go from state 1 up to here, and then we go down to there. So let's call this step 1 and step 2. So we go up here and down here, and then we end up at state number 2 via a 2-step process. Everybody okay? So this would be the enthalpy change for state 1 this would be the enthalpy change for state 2. So Hess's law tells us for thermodynamic state functions that the overall delta H is just the sum of each individual step to get there. So this would be delta H1 plus delta H2. Right? So maybe we don't know this. Maybe we can't run something experimentally, some process or reaction. But let's say we know delta H1. Somebody ran something, we find it in a thermodynamic table, and we find delta H2. We find that in some thermodynamic table. And we add those two together, which gives us the overall. We can calculate it indirectly. Woo-woo! Don't have to go in lab and do it and all that fun stuff. But let's say we can't find this, right? We can find that, but not this. So let's say we can find something that adds up to those. So we go to there, and then we go to there, and then we go to there. So let's say we do this in 3 steps. So we got step 1, step 2. So we can get it in 3 steps because we couldn't find that value, right? So this would be delta H1 in this scenario, delta H2 in this scenario, and delta H3 in this scenario. So this is the second pathway. So let's say we can find these 3 values in some thermodynamic table. Hey, so we know, because enthalpy is a state function, doesn't matter how we get from state 1 to state 2, doesn't matter. Delta H overall is just, whoo, that pen smells bad. That is going to be equal to the enthalpy change of the first step plus the enthalpy change of the second step plus the enthalpy change of the third step. And either way we do it, this number will be the same if it's the same process. It's a great little trick you're going to see over and over and over again. So I got to teach you a couple rules here, though, because when taking these, say we find them in some thermodynamic tables, and say it's a reaction, we want some overall reaction. But a lot of times, some of the equations we find in the tables aren't written the way we'd like them to, right? Because we're not the one that published them. So maybe they're backwards from what we want, or maybe they don't have the right stoichiometric coefficients. We want 2 moles of something, but they only have 1, or they, you're like, it's so frustrating. So we're going to have to manipulate the equations that we find in the thermodynamic tables so that when we add them together, we get the overall process. But there's some rules to follow, because when you mess around or manipulate an equation, right, so in the way it's provided for you will have some enthalpy change value. But if we change the equation, if we reverse it or change the coefficients, we're going to have to alter the delta H value for that. So there's some rules I have to show you to do this. Let's do this on the next board. All right, here's some important rules to keep in mind. And unfortunately, next semester, when we get to equilibrium and kinetics, the same idea applies, but the rules are a little different. Erg! Right? So it is what it is. But we're sticking with just thermodynamics for right now. So enthalpy is an extensive property, right? Remember, extensive versus intensive. Intensive properties are independent of the amount of a substance, like density or whatever. But enthalpy is an extensive property. It matters how much you have, right? If I have 1 mole of a substance versus 2 moles of a substance, that's going to make a big difference. If you have more of a substance, the delta H value is different, right? So how do we account for that? So if we take an equation, find some equation that has a delta H value in some thermodynamic table, but we have to manipulate the equation because the coefficients aren't right. So let's say we have to multiply it by 2. We got to double the recipe or triple it or divide it by 2, which is multiplying by 1/2, right? Anything. We have to multiply it by some coefficient. Let's call that n, right? Well, we're changing the amount of the substance. Oh, no! H values are extensive, right? Delta H values are extensive. So if we multiply an equation, say, by 2, we're going to have to multiply the delta H value by 2. If we multiply an equation by 1/3 or divide it by 3, we'll have to multiply it by 1/3 or divide that delta H value by 3. So just keep track of that, right? And we're going to be doing a lot of manipulation, maneuvering equations so it's like solving puzzles. I'm going to do a kind of a simple example first. And if I have time, I'll do a second, more complicated one on the same video. If not, I'll do a second video just for the complicated problem. And it's pretty simple to do, right? Just keep track of it. Another issue, which is just kind of a subcategory of this, but if I take an equation and reverse it, right? It's the same, like we talked about enthalpy of, vaporization versus condensation. They're the same numerical values, just the sign is different. Okay, same thing's true with delta H reaction. So if I have a reaction in the forward direction with a particular delta H value, let's say it's endothermic, if I reverse that equation, the delta H value is exactly the same, it's just negative now. Right? So if you reverse an equation, you have to change the sign on the delta H, and we may or may not need to do that. So maybe the equation we find in some thermodynamic table is this way, but in order for us to get the answer we need, we're going to have to write it backwards. We need to change the sign on the delta H. All right, so keep these two rules in mind, and then remember Hess's law. When it's dealing with heat, they call it Hess's law of I think it's constant heat summation or something. Most people just call it Hess's law, but when you're dealing with enthalpy of constant heat summation, the overall process is just the sum of the individual delta H's. So what we're going to do is we're going to be provided equations with delta H values, heats of reaction. We're going to manipulate those equations so that when we add them all together, we get the overall equation of interest. Problem is, if you manipulate equations, you got to manipulate the delta H value. So we're going to change all the delta H values accordingly. Then we can add them all together to get the overall delta H. It's like a big game, like a big puzzle. Let's do one. Yeah, we'll do a simple one to start. How about that? You ready for our first puzzle? Kind of like when I was a kid, I used to buy these books. You do word searches and stuff, but there's one called Logic Problems. There's 5 lions and 5 tigers, and each has a different name, and each one comes from this place, and you have to figure out which one associates to what, right? With these logic, I used to love those things when I drive across country as a kid. Turns out it was on my graduate record exam. They had these little logic problems that were kind of like it. It's a particular way of thinking, very deductive reasoning, which we use as scientists, right? So anyway, I got off track again. So here's this is a very simple one. So what is delta H reaction? And let's do this at standard conditions. Let me add my little degree symbol. It could be at standard or non-standard conditions, right? If you have these at non-standard conditions, that's fine, right? Depending on what somebody did in a research laboratory and published in some journal article or some thermodynamic table, it may or may not be at standard conditions. That's not the point here. The point is using Hess's law to figure out some unknown delta H of a reaction. So let's say the solid sulfur plus the oxygen gas, or the combustion of sulfur giving sulfur dioxide gas, we want the standard delta H reaction for, but let's say we can't find it in some thermodynamic table, or we can't do it in lab properly to get to experimentally measure it. So let's do it indirectly. Let's use Hess's law. Let's say we dig through some research articles or some thermodynamic papers or whatever, and we find that the combustion of the sulfur dioxide gas here to form sulfur trioxide gas, we find that one is a negative 198.2 kilojoules. Hey! Okay. And then we find that the sulfur solid plus 3/2 moles of oxygen gas gives you sulfur trioxide gas. And we find the delta H value for that at standard conditions is negative 395.2 kilojoules. Oh, okay. So just provided 2 equations, right? Most commonly on exams, you'll find 3 equations, sometimes 4. It gets a little hairy at 4. Obviously, the more equations you have, it kind of, I wouldn't say exponentially gets more challenging. It just gets more fun. So let's go through the thinking process here. There's no specific way to do it, but this is how I like to do it. Here's the equation of interest, right? I've got sulfur solid, oxygen gas, and sulfur dioxide. So I'm just going to start on the left-hand side. I'm going to look at sulfur solid. I need to get, do you agree, 1 mole of solid sulfur on the left-hand side, the reactant side. Agreed? So let's take a look at the equations provided. Let's see if we can find an equation that has solid sulfur. But if I find that solid sulfur in multiple equations provided, that's like one equation with 2 unknowns. It's too hard. So I just kind of skim through and see if I can find an equation that's provided and it's the only one that has that particular species. So let's look at equation 1. There's no solid sulfur in there, so that doesn't help me. But there is in the second one. Hey, and it's on the left. Is it on the right side? Is it on the right side? Is it on the correct side? Yes, it already is. So I don't need to reverse it. Yay! All right, so I can keep the sign on that the same. Is it the correct stoichiometric coefficient? 1 mole, 1 mole. Well, isn't that nice? Right? I told you this was an easy one. So equation 2 we're going to keep the same. I don't need to manipulate it. I already have the correct species on the correct side with the correct stoichiometric coefficient. But if there had been a 2 there, I would have had to like multiply it by half. If it was on this side, I'd have to reverse it, right, and change the sign. So we're cool. Let's take a look at equation 1. This is the funnest part for me, figuring this out. All right, so let's take a look at the next species, oxygen. Ooh, both equation 1 and 2 have oxygen. No, I skip it. Good luck with that one. It's not going to work. All right, so let's go to SO2 gas. All right, I see sulfur dioxide gas in equation 1, but not equation 2. Yay! Okay, so I can manipulate equation 1 to make sure I get 1 mole of sulfur dioxide gas on the right-hand side, the product side, correct? And then I'll add these together and, oh, please, let the oxygens work out. Is sulfur dioxide in equation 1 on the right-hand side? It's not, so I need to reverse it. So we have to reverse equation 1 in order to get the sulfur dioxide on the right-hand side. Is the coefficient correct? There's a 2 in front of it in equation 1, but a 1, oh, it's not the right coefficient. I need a 1. So how do I go from a 2 to a 1? I got to divide by 2 or multiply by 1/2. Or you could say divide by 2. So based on this, delta H1, if we reverse it, we're going to change it by the sign and multiply it by 1/2. So it'll be negative 1/2 of negative 198.2 kilojoules. Got a little squishy there. So we take the negative 198.2 kilojoules, change the sign because we reversed it, and multiply it by 1/2 because we had to multiply it by 1/2 to get from a 2 to a 1. Now, equation 1 we didn't change. Equation 2, excuse me, will just stay the same. So I've run out of room. So on the next board, what I'm going to do is I'm going to rewrite equation 1 and rewrite equation 2 based on the manipulations. Then I'm going to add them together to get this big, long overall equation. I'm going to simplify it, cancel out like species on either side. And then the net result, the overall equation, should equal that. If it doesn't, I screwed up my manipulation somehow. So if it matches it, I always confirm that first. So I'm going to manipulate my equations, add them together, remove like species on either side, and then make sure it confirms the overall equation. If it does, then I'm just going to add those together. That's it. Hess's Law heat summation. Constant heat summation. Boom, boom. So I'm out of room. So do this for me. I'm gonna pause this and erase this board, but I want you to rewrite equation 1 by reversing it and multiplying it by 1/2. See what you get. And take equation 2, but just keep it the same, and then add those two together to get an overall equation simplified. See if you can do that before I do. Be right back. Is this what you got after you manipulated the equation? So equation 1, remember you had to reverse it, right? So the SO2 goes on the right, the oxygen goes on the right, and the SO3 goes on the left, and you multiplied everything by 1/2. So the coefficient that used to be a 2 is now a 1. Coefficient used to be a 2, now it's 1. Coefficient used to be a 1, now it's 1/2. Right? So multiply everything by 1/2 and reverse it. Equation 2 we didn't change, so I just rewrote it. Sulfur plus 3/2 oxygen goes to SO3. Let's add these together. This will be our overall equation. Now, a lot of times, if I'm on my own, I just do this in my head. But I want to write this out so you can see what I'm doing. Here we go. Let's do this in blue. So let's take everything on the left-hand side. So let's take this SO3 gas and the solid sulfur and the 3/2 oxygen. Would you agree that's everything on the left-hand side of the arrows if I add these two together? Okay. Now let's do everything on the right-hand side. We got SO2 gas, 1/2 oxygen, and a sulfur trioxide. Squish. Right, so I just take everything on the left, everything on the right. That's an overall equation. Now let's take a look and see, are there things that are exactly the same on both sides? Well, I got an SO3 gas here and an SO3 gas there. You see that? Would you agree that those are going to cancel? I got 1 mole of each, so those are going to cancel out. Right on? That's a good thing because there's no sulfur trioxide in the equation that we're after. I've got a solid sulfur on the left. Do you see one on the right? Nope, so that's going to stay the same. I got 3 halves oxygen. Do you see oxygen on the other side? I do. But see, I got 3 halves here and a half there, so they don't completely cancel out. So if I subtract a half a mole on each side, this will go to a coefficient of 1, and that disappears, right? 1/2 minus 1/2 is 0. 3 halves minus 1/2 is 1, correct? And then I got an SO2 on this side, but nowhere else. So the net ionic equation, not net ionic, net equation. This is the net overall equation. I'm just simplifying. So let's call that simplified. Let's just, instead of saying net, let's say simplified. Let's simplify it. And when we're done, it had better match that. I'm looking for that on exams. You've got to confirm it. Otherwise, you're just guessing. So the sulfur trioxide's gone, so we're going to get solid sulfur right there, plus 1 mole of oxygen gas right there. And we've got 1 mole of sulfur dioxide gas there, and those are both gone. Does that match? It does! Yay! So we can move on. If that did not match, you manipulated things incorrectly. All right, that would be a problem. So now we can do delta H, the Hess's law of constant heat summation. So the delta H reaction at standard conditions for that will just be the sum of these. Right? That's Hess's law of constant heat summation. So I'm just going to add those two together. I took the numbers out. I ran out of room. So let's take the first one. Let's take -1/2 times delta H1. That was the -198.2, I think, right? And we're summing it. So let's do the second one, which we didn't change at all. So we could just take delta H2 there, which was, what was that, -395, -395.2 kilojoules. And that's it. And since we're adding, we're limited by the largest absolute uncertainty here, so tenths. So we're going to be to the tenths place either way. I haven't done this ahead of time, so let's see what we get here. But you get the idea, right? We just took the original delta H value that was given to us, and the new one after manipulation, we reversed it, times it by a half, or divided it by 2. And the new delta H2 was the original delta H2, because we didn't change it at all. So let's take 198.2 and divide that by 2. That gives me a 99.1, and that, in negative times negative, that's going to be a positive value. And then subtract 395.2, you get 296.1 on your calculator there. Wow, I don't know if you can read that. So negative 296.1. And there's no non-rounded value, so there's no intermediate value. Okay, so since we reversed it, that negative times that negative makes it was exothermic, now it's endothermic. And so that just brings that down, the negative down a little bit. There you go. That's it. That's for a simple one. To get the basic process, right? Take what you're given, manipulate the equations, right? Based on, find an equation where just one of the either reactants or products in the reaction of interest is in just one of the equations provided. That allows you to manipulate it. And then adjust the equation, write the new equations, add them together to get the overall, simplify it, and see if it matches. If it does, manipulate your delta H values appropriately and just add them together. So I think if I do a tougher one, it's going to make this video go too long. So I'm going to stop the video here, and then we'll do a more complicated example in a separate video. Welcome to Hess's Law. You're going to be doing it a lot, gang.